CRISP-DM stands for Cross-Industry Standard Process for Data Mining. It is a widely used human-centered framework for organizing and structuring the entire data mining process. And unlike the black box algorithms that are used in certain data mining methodologies, these include neural networks and support vector machine, CRISP-DM is designed to ensure transparency and interpretability in the data analysis workflow. Data mining itself is about uncovering the hidden patterns, meaning repeating structures and relationships or connections between variables in a data set. It has the goal of building models that predict future outcomes or that classify new data. CRISP-DM provides a structured, iterative approach to producing human-driven insights. And this is, again, in contrast to the more opaque, complex methods that optimize for prediction accuracy, but that often come at the cost of transparency, which becomes a source of particular tension when used in sensitive fields like healthcare and law. CRISP-DM unfolds across 6 phases. The first is business understanding. So this is when the data analyst starts by understanding the business problem, setting objectives, and defining project requirements. Data understanding. This phase involves collecting the initial data, and it's followed by exploring it to discover data quality issues, identify patterns, and uncover relationships. And this phase is actually closely aligned with exploratory data analysis. So where the data analyst is inspecting the data set and formulating hypotheses and getting a sense of the data's overall structure. The third phase is data preparation. And this step is about cleaning the data, handling missing values and incongruencies, transforming features, and ensuring that the data is actually ready for modeling. And this is essentially the hands-on work of refining the data set for future analysis. Modeling is the next phase, and in this phase, data scientists select the appropriate modeling techniques based on the earlier insights from the phase, the EDA-like phase. For example, if the relationships discovered in the data are nonlinear, then the techniques that you would go for would be something more like decision trees or neural networks. And this is where the hypothesis about which variables and relationships matter starts to take form. And this helps to guide the modeling choices. After modeling comes evaluation. This is when the analyst assesses how well the model meets business objectives and whether it accurately predicts or classifies based on the desired criteria. And if necessary, adjustments are made before final deployment. And then finally, there is deployment. And in this final phase, the model is integrated into the business process and the results are put to practical use. So time series analysis is the process of understanding and modeling data points that are collected over time, where time is always the independent variable. Before forecasting, it's essential to analyze the structure of the time series to ensure that it's actually suitable for prediction. And first, we need to identify the underlying patterns in the data. A time series is a sequence of data points arranged chronologically in chronological order. And when it's plotted, patterns such as trends, seasonality, and randomness begin to become apparent. The 3 main patterns in time series are stationarity, autocorrelation, and seasonality. And while there are shorthand ways to recognize these patterns visually, it is very important to pair the visual intuition with a mental check on what's actually varying over time. So first, with stationarity, this is a statistical property of a time series, and it means that the statistical properties, like the mean and variance, stay constant over time. So while the data might still be random, that randomness is actually consistent. So this means the relationships within the data can actually be modeled. In a stationary time series, we can expect that past patterns are predictive of future ones. So for example, if we took some housing prices as a data set, if the raw data shows that there's an upward trend, we could naively predict that the prices are just going to keep increasing forever, when in fact, the trend could be driven by external forces like inflation or population growth. So to make this series stationary, we would often use a technique called differencing. And this is where we subtract each value from the previous one. This shifts the focus from the absolute values of the housing prices to the change in values over time. So example, like price fluctuations. And this allows us to forecast changes rather than assuming a fixed increase. The other two patterns are autocorrelation and seasonality. And while both can look visually similar, you can see predictable fluctuations at regular intervals. They are actually very distinct in their underlying causes. With autocorrelation, past values are correlated with future values. And it's not because the past values cause future values, it's because they suggest a kind of statistical momentum. So for example, electricity usage tends to follow a daily cycle that's based on human behavior. People use more electricity during certain times of the day or week, and so the data shows consistent patterns of correlation. It's a bit like the system has a kind of memory, and that is what engenders this kind of statistical momentum. Seasonality, on the other hand, refers to fluctuations that are driven by external calendar-based cycles. So these patterns often make a time series non-stationary because the fluctuations can cause the mean to change. For instance, retail sales might spike during December due to holiday shopping. The seasonal fluctuation in shopping behavior doesn't stem from the past values themselves. December of one year is not influenced by the December of the previous year. But what is influencing it is an external calendar event that repeats at the same time each year. So data ethics. Data ethics is crucial because data is generated either by humans or human-designed machines and algorithms, and both of these carry biases. To ensure fairness, accuracy, and accountability, organizations should adhere to several key principles. The first is transparency. Organizations must clearly communicate how the data is collected, processed, and used. This includes disclosing the potential biases, the limitations, and the methods that are used in order to ensure fairness. Second is fairness and bias mitigation. Bias in data can arise in many, many ways. The first is collection bias. So this is when data is passively collected from unverified sources. And as a result, it may not be representative. So companies should actively assess data sources and ensure that there's a diversity in the collection. An example of collection bias would be like relying on TripAdvisor customer reviews to decide on a hotel when, again, with the passive collection method, what happens is you really only have people with strong opinions that are leaving reviews usually, so this skews the data. Second one is sample bias. If a data set does not proportionally represent subgroups within a population, the results will be skewed. Random sampling methods and stratified sampling help ensure a much fairer distribution. The iconic example of sample bias is the 1936 Literary Digest poll that incorrectly predicted that Landon would beat Roosevelt in the US president elections because they only sampled wealthier Americans through automobile and telephone records. And this was not representative of all voters, clearly. Exclusion bias. This is when important features are left out, whether due to oversight or assumptions about the relevance. And these results can therefore be very misleading. Unlike sample bias, which is something that happens during the data selection, creating that representative sample, the exclusion bias occurs when a key feature is missing. So for example, you have a medical study on heart medication that excludes participants over 65 because you just assume that the drug is going to work the same for all ages. And this will lead to inaccurate conclusions for elderly patients because they were excluded. Measurement bias. If data is collected inconsistently or with flawed instruments, inaccuracies will propagate. Standardizing measurement techniques is very key. So for example, training fraud detection models on data labeled by different experts, that would be a problem because there could be some of those experts that are stricter than others, and this would create inconsistencies in what gets classified as fraudulent and modeled. Privacy and security. This is another big one. Privacy and security, while these are often mentioned together, they actually serve distinct functions. Privacy governs who has access to the data, what data can be collected, and how it can be used within an organization. This involves policies on data handling, user consent, and ethical data sharing practices. Security, meanwhile, refers to how the data is protected from breaches, leaks, and unauthorized access. This includes encryption, authentication controls, and cybersecurity safeguards. And finally, the next principle of data ethics is accountability. Ethical data practices, they require ongoing oversight. Companies should be regularly conducting bias audits, ensuring compliance with regulations, and involving diverse stakeholders in the decision making. By embedding these principles into data processes, organizations can foster ethical, trustworthy, and responsible data use. To raise concerns with my manager about measurement bias in a predictive model, I'd first pinpoint exactly where the bias emerged. So I'd want to be very clear about identifying which flawed inputs are leading to the skewed outputs. Measurement bias could stem from inconsistent data collection, where variations in criteria or labeling practices are distorting the model's accuracy. It might also result from instrument errors, such as incorrect weighting of key variables, for example, credit scores. Additionally, there might be human judgment inconsistencies, like differences in analysts' experience levels. This could lead to uneven benchmarks, and this would influence the model's decisions. To prevent this in the future, I would propose standardizing the data collection practices through clear documentation and guidelines, ensuring that all the inputs follow a much more consistent methodology. Regular calibration sessions for analysts would help align decision-making standards, while automated checks could also help to flag inconsistencies in key variables before they enter the model. These tools would improve reliability, reduce bias, and ultimately lead to more accurate, fairer predictions. All right, so regression and classification models are what help us to bridge the gap between data analytics and data science. We're moving from the data analyst's interest in more like descriptive insights of the past to data science's focus on predictive capabilities. The key distinction between the two models is that regression predicts continuous outcomes in the form of numerical values, and classification predicts discrete categories, so qualitative labels. So to illustrate a bit of the difference use cases between the two models' use cases, I'm going to walk through a scenario. So let's say we're predicting housing market outcomes, working for a real estate agency, and I have a data set that has features such as square footage, number of bedrooms, neighborhood, age of the house, and the proximity to schools, etc. So if we took the regression approach, the question would be, how much will this house sell for? And so we've got a target variable, which is the sale price, and this is a continuous value. And so an example of a regression model we use here would be linear regression. And let's say that the output gives us that based on these factors, all these different factors I just mentioned, we predict this house will sell for $500,000. And so we used regression here because the price is a continuous number. It could have been not $500,000, it could have been like $425,000, etc. Using the classification approach for this scenario, the question, instead of how much will this house sell for, it would be something more like, will this house sell within 3 months? Yes or no? Here, the target variable is yes or no, a binary classification. And an example model here would be like logistic regression or decision tree classification. And here we might have an output like, based on these factors, we predict a 90% chance that this house will sell in the next 3 months. And so we use classification here because the output is categorical. It's either yes, it'll sell in 3 months, or no, it won't. I think that it's very important that rather than seeing regression and classification as fixed steps that only belong in particular parts of the predictive analysis pipeline, they're actually fundamental ways to structure data relationships. And the choice depends not really on a rigid context of use, but it's on how the problem is framed. It's a lot like thinking about different maths. You can use algebra to describe movement, kinematics, but you could also use calculus for that. So translated to this context, you can use classification for fraud detection, for example, but maybe a regression model could also provide insight. It all depends on how you frame the problem. So it depends on how we frame the problem for the housing scenario, whether the question was, do we want to know how much it will sell for, or whether the probability that it will sell in a certain time frame. Maybe for example with the fraud, for fraud detection, for instance. So same predictive challenge, 2 approaches. So let's say that we want to predict the relationship between a client's age and fraud alerts. So with the regression approach, this would be a continuous outcome. You could use linear regression to predict how many fraud alerts are expected for a given age. And so the output would be a continuous value. How many fraud alerts? Classification approach, you would reframe the problem as a classification task. So will this client trigger a fraud alert? Yes or no. And so here you'd use logistic regression versus linear regression, and you would estimate a probability. So this is useful when decisions need to be binary, like flagging high-risk individuals for review. So why choose one over the other? If you need a specific number of fraud alerts, you go with regression. If you need a probability of fraud for classification into risk groups, you would use classification. Okay, thanks.